Marcus. Hey, good morning or good afternoon, wherever you are, Hong Kong, Taiwan, Singapore. Well, places I haven't been to. I go like it's cool how we can be connected to around the world to think about computational thinking and coding. And so I just have to talk a lot because I'm terribly nervous whenever I give a talk because I really only have a few slides. What I want to show you is I actually want to program something for you. And so I just come up with new titles that I'm going to talk about, but really what this is going to be is a demo about interesting things that we can do with programming. So as I was on vacation last year in southern France, I found this interesting title. I just know a little bit of French, not enough. The little bit of French said vide grenier, which apparently means something like empty your attic. And that's a flea market. And so on this flea market, I'm a guy. I love tools, kind of steel stuff, heavy stuff, and carry it all the way to here. So I thought, well, this is like the archetypical picture of a tool. When you think about a tool, it's a hammer. It has a purpose, it has a function, an input, nail. There's another tool. It just happens to be the inverse function. This one it also has an input, a different one. And I kept thinking to myself as I was in that vide grenier that we talk about programming languages, programming as a tool, as something that we use, something that we command to make the computer do something. And I was thinking to myself whether that is really kind of my experience with computing, or whether it would be something more. And the something more is that when we really get lost in the things that we do, we immerse ourselves into these things, and somehow we are part of the thing, and then the thing is all around us, and that's kind of the idea of a medium. So this is what I want to show you today, kind of my experiences about programming as a medium. I'm going to show this to you in this language that I make, that is called Snap. Build your own blocks. Now, Snap really is very similar to Scratch. Oh, wait. Do I need to share?
It was sharing your audio, just not the screen.
Okay.
This camera, now it's sharing.
It's sharing the screen again? Okay. Snap, it's an interactive visual programming environment. It runs in the browser just like Scratch. It combines the visuals of Scratch, the blocks, with the semantics of Lisp, of Scheme. And the reason it does that is so we can use it for UC Berkeley's Introductory Computer Science course for non-CS majors, the course for CS for everybody. And that course is called, get this, The Beauty and Joy of Computing. That's what every introductory course at every university should be named. The beauty and joy of something. If you're not having beauty and joy, you're doing it wrong. And it's also used at colleges and schools and high schools around the US. I'm not working at Microsoft, but Microsoft uses it. Their outreach program, they sent me some t-shirts. They were kind of 2 sizes too large, so it was a motivation for me to lose some weight so I could wear it today. It's always very important for these languages, since the stuff that you program in is actually the label on the blocks. Very important for it to be translated in different languages, so it can be used in different countries. That's one of the traits of blocks-based programming that is really interesting, that the language itself gets translated. It's not just the IDE, the menus, but the language itself. It is quite a large project, not nearly as big as other projects, but roughly around 625,000 user accounts. and they kind of made about 5.7 million projects. I think that's probably with Scratch in one day. But mind, this is a college and high school. It's all free and open source, so please don't be alarmed that I'm working at SAP. This is all free and open source. There's no logo on there. This was funded by the National Science Foundation. And so this is the team. It's not just me. There's a team at SAP. We're really, really lucky that SAP funds this and that SAP funds this kind of research. That's Bernard Romagosa in Barcelona, Jepka Hügler in Heidelberg, and myself in Tübingen. And there's a corresponding team at UC Berkeley, my colleague Brian Harvey, Professor Emeritus, also Dan Garcia, another teaching professor, and Michael Ball, a lecturer. We're kind of a core team, but it's free and open source. There's an online community around it with lots and lots of contributors from around the world. And so these are all the slides I have. I already showed you my tools. I'm done. Actually, no, let me show you Snap. Where is it? This is what it looks like. Kind of like Scratch used to look like at version 1. I really like that look because I worked on that. So I wanted, when I rewrote it, I wanted to keep that look. And so what we need for the introductory computer science course at UC Berkeley is we need to be able to make tools. We need to be able to make functions, make our own blocks, build our own blocks. That's really the idea. So you know how this works is I can make a block. And this was kind of the original design. I can make a block. I can make any block in the system. I can select the category. For example, I want it to be kind of a mathy block. I can say, you know, it should be double a number. And so I can make any kind of block, not just command blocks, but also reporters, function blocks, right? So I'm going to make a reporter. I'm going to say, okay. So what's different from Scratch is that now this opens in the block editor, and I can say, okay, now I want to turn number into an input. I can also specify kind of some hints that this is going to be a number input. And now I already have the block here. If I click apply, the shape is already there. On the outside, the input is just a slot. At the inside, it's a variable. And I can enter a formula here. What this block should return, it should return the, you know, the number plus the number. This is how I define the block. I say apply, and I can test it now. I can say double 5, that's 10. Double, somebody always has to write 42 for some reason. Douglas Adams, okay, so that's 84. And so this is how data gets passed into a function. On the outside, it's a slot. On the inside, a variable. And so far, so good. And we can make functions, right? And now the interesting thing happens that, you know, data comes in different forms. What if we have, for example, a list of data? So I'm just going to be kind of really nerdy. This is how we make a list. The block that makes a list. What if we want to apply, you know, our double function to that list? So the usual way we do this is, you know, with these computational thinking concepts that you all have to learn. So we have to learn about loops. So we have a for loop. We have that. Oh, we probably also need to learn about variables. That's also a very important concept, right? So let's say here, that's my list. I'm going to set my list to this list. I probably also need to have an output list. This would be a result. You always have to remember to initialize your lists. Otherwise, the program is not going to work. Then I'm going to enumerate. I'm going to say for I equals 1 to probably the length of my list. I want to add something to the result. And what I want to add is double the thing that's at index, right? It's always important in Snap indices. It's the item I of my list to the result. And when I'm done, I want to report the result. Okay, so this is what kids have to learn. Let's try this. Oh yeah, and I'm getting this new list, right? So this is computational thinking in a nutshell. And it's crap, right? I mean, it's no good. I mean, this is how you learn how to program. And look at all this cognitive load there. There's, many blocks. You need to remember that, it's an indexed list. You need to learn that, in order to get an element out of that list, you first need to get a number, and that number is inside some variable. You have to think around many corners. You have to know that lists in Snap start with 1, whereas, real computer science, they start with 0 or some other. And that's all this kind of load, all this secret knowledge that we think is essential, and that is somehow how computer scientists think. And that makes it just very hard just to double all the numbers in a list. I know all of this. So clearly there must be a better way. And of course, you all know the better way. It's been invented in the 50s and 60s. There are several better ways. And the better way is higher order functions, right? It's a function. So you have built-in higher order functions in Snap. One is map. Map has one of these rings. And rings are what makes Snap special. A ring, now if I put the double block into the ring, what happens is when I have a ring and I put something in there, it doesn't get evaluated, but instead it returns a function. And what's inside the ring, whenever there's an empty slot, that's kind of the idea of new math, an empty slot, that's like we pronounce it, that's a formal parameter that doesn't have a name. So we don't have to give variables a name, so I can now take this list, and what goes into the empty slot is, whatever is inside that list. So if I click on this, I get it in one step. That's the power of higher order functions. No indices, no loops, just a simple expression. And anything can go into here. So this is a ring. A ring is really the most powerful. A ring really is this. It's a lambda. And this is why this is our mascot. You might know the mascot. It's Gobo from scratch, right? But got a different hairstyle. The hairstyle is the lambda. So this is what Snap is. Snap is scratch plus lambda. That's really what it is. So inside the ring, we can write anything. So we can double it. We can also say, join. Hello, Don't say X, don't say N, because then kids will think that, it's not a variable, but it's an unknown, and you need to kind of, figure out, but the unknown is, it's just a placeholder. We can put complex things in there, like we can say, okay, what if, the, can nest stuff in here. What, the mod 2 equals 0. Now, what comes out of this is different data structure. It's a Boolean value that tells us whether a number is even or odd. And we can even use this to make more complex stuff. So we have a list block. So we can put in a list with a double block. So now we get a list of lists whose first item is the double. We can expand the list. And now we have 2 empty slots. So the number goes into both empty slots. So what we get is a table. A table, first column is the plain number. The second column is the double number. And a list, a table in Snap is really just a list of lists. And that's a powerful thing, because then we can also use these higher order functions on tables. There's just one concept that pervades the thing. So higher order functions are cool. You can program like this all your life. You'll get a job in the industry, but your life will change If you don't program like that, your life will change if you program like that, because that's actually how they do it. And I'm going to show you one more thing in the industry. If you work with data, you don't even use higher order functions all that much. And we had this idea when we did a workshop with teachers, really, is when, I asked them, how do you apply this? And they said, can't we just do this? I said, no, you can't, because it's a different domain. One is the domain of a scalar. It's a number. And now here is a vector. It's a different domain. You can't, wait, why can't you do that? Because Ken Iverson and APL showed in the 60s that yes, you can totally do that. And anybody, if you work with Python nowadays, NumPy anybody, nobody in data science does this. They don't even do that. They do this. Of course, you should just extend the domain of mathematical operators to also work with any dimensional data. So yes, it's a list, and we can use all these functions with any dimensional list, and that's what we call Python blocks. Now this is interesting because look at this. One thing that's interesting for kids is also to find motivation to find yourself in your program. So this is why in Scratch and Snap you can take a picture of yourself. You're an old dude like me, you may do the old kind of tongue thing. So we can look at this picture. This is the costume that I made. It's the camera costume. I can get the width of this costume. I can get the height of the name. I can get the pixels of this costume. And if I get the pixels of this costume, I'm getting a table. And a pretty large table. 172,800 rows of 4 columns. So numbers, anybody know what these numbers are? The RGB alpha values of each pixel. So all of this is really just a list, right? It's just a list of lists of 4 items. So I was just telling you that we can use these functions on any data. So what if we just double this whole table? And mind you, this is large data. This is 172,000 entries. Try doing that in your math entry guide. So boom, it just works. So now we've just changed every number in this thing. And oh, wouldn't it be nice to actually see what it does? So I'm going to switch to that costume. What do you think is going to happen? Look at that. We just made the picture brighter because we increased every value. And so this is a concept. If you want to talk about concepts, don't talk about groups of variables. Talk about what makes media, what's the effect that an operation has. And if you want to talk about modern media, don't just use a static picture, but use a video. So I'm using the video on the stage, and now I'm doing this, and I can use this inside a forever loop. Now I have a video effect actually for motion video, and now I can, I can play with this. So what if instead of double, I'm saying, okay, I'm multiplying all these pixels, not just with a number, but with a vector. So if I'm multiplying with a vector of, say, 2, what I'm now getting is only the first column is being doubled, and the others are going to stay the same. So let's try this. So now it's kind of more reddish. Doesn't kind of look. What if I just put 1 in here? Oh wait, it's plus. I'm saying double. Just okay. So now I can make different color effects of myself. I can even kind of go so far and say, okay, what if, you know, I'm just keeping it like this, but I'm saying 255 minus whatever is in here. What do you think we're getting now? We're getting a negative. And so these are concepts when we think about data and when we think about applying tools to data, tools that have individual function, and we can use this to analyze the world around us and to really think about media. So one thing that is always very motivational is, you know, physical computing. See something happening in the real world, interact with the real world, measure the real world, manipulate the real world. So let me do one more thing. So this is going to be a little bit tricky, but I hope it's going to work. Here's the microphone volume. That's the volume of my microphone. And so kind of, you know, what teachers like to do is, you know, we say the microphone volume. We always say that. So now you see the microphone volume being picked up. But also the microphone picks up not just the volume, but it picks up, you know, actual numbers. So these are the actual samples coming in at very high, critically high speed. We're again talking about big data. That's data that's coming in very fast. Now it's just data. We should be able to do something with it. Let me actually try to plot it. So let me try to say, you know, I want to now use just a for each item in the samples. I want to make a little variable that is going to plot this. This is going to be a slice. I'm going to set the slice to the ratio of the stage width. That's 480 pixels by the size of my buffer. I am going to set the x to 0. Then I'm going to change, go to the x position of this arrow plus whatever the slice is, and go to the y position, whatever in the samples is. I want to do this very fast because data is coming in very fast. Before I do something, I want to set the pen down. Then I'm going to lift the pen up when I'm done. First, I'm going to clear it. And I want to do this forever. Okay. Let's actually try this. Do we see something? It takes a while for my microphone. Okay. Oh, maybe I shouldn't set it to 0 because that's the middle of the stage, but you know, minus 240. Okay, now I'm seeing a line. Not much is happening there. We saw all these numbers, and that's because those numbers are just from between -1 and +1. So this is another interesting concept. We want to scale this. So I'm scaling this. It's the item times, you know, let's say 100. Oh, and now what we're getting is, you know, something where I can actually see the sound that is being picked up by my microphone, and I see a wave, and I can actually see something else that, you know, when I'm talking softly, the wave isn't doing as much. Whereas when I'm screaming, it is getting really loud. I can also see something, you know, I can interact, you know, with musical instruments with that. And I can do something else. So this is how we can measure and visualize data just using very simple things. I can actually, let me duplicate the script and just change something. I can also get the spectrum. And the spectrum, I want to use this. Oh wait, I mistyped here. So now what I'm getting is a visualization of the frequencies of what I'm talking. This is a spectrogram. And I can see how sounds are composed. You can see my voice. So every one of these peaks is a frequency. And I can see, for example, that I take this ukulele. You see certain spikes there. These are the overtones. And the overtones are different for kind of every sound I make, because the combination of overtones is what makes the sound interesting. So if I take my harmonica, you're going to see very distinct spikes. Whereas if I whistle, even though I'm trying to whistle really high, you just see it's just on the left. So all the stuff that's to the right, you can't really hear, but it still contributes to the sound. And like if I had this tuning fork, I should see just one distinct spike. Yeah, sort of. It's very, very soft. So this is something, when we talk about physical computing, what we often do is we dish out, some circuit boards and we say, this is how a computer works. And we do robots follow a line in the car. And that's all nice and well, but we need computers to program these things. Because you need to plug in the little computer into the big computer, then you program it on the big computer and say, wow, now I programmed the smart computer. Now, imagine, all the setup you need to do to assemble the damn thing with a class of 30 people. Whereas they already have computers. The computer, has a microphone, it has a camera, it is perfectly fit to interact with the physical world. That's what computers do. And so just one more thing. If I want to see these over time, let me get this in here. So now I'm doing the very same script, but I'm plotting it as a sort of a sonograph where I'm just using the saturation of the color to show the spikes. And now we can actually see kind of melodies over time. And you see my voice is more complicated. You kind of see the combination of the overtones, and you see them more distinct again with this. Okay, so we can build our own tool, and that to me kind of is the first really distinctions why I think it's a little bit derogatory to talk about programming as a tool, because this is really something where we can take it to the meta level and we can explore the world, and not just the mathematical world, but the physical world, and interact with it. And once we've explored it, we also want to interact with it. So we can look at these things. Oh, and now I think now is the time where I need to stop sharing and reshare. Now I need to reshare the Chrome tab so I can share the tab audio. Yay, let's try this. So I'm gonna record a sound. I'm just gonna record one word, and you guessed it, it's gonna be snap, snap. Can you make it so we can hear that? Okay, so I can play back snap. Wait, and now I should, I guess, mute this. Okay, is this better now? So snap. So this is when I play it back at normal speed. I can play it back at different speeds though. So I can put in any number here. So this is now snap. Ta-da! This is kind of fun. What if I play that? So by just manipulating this movement, I can control the speed and thus the pitch of the stuff that I recorded. So I can use this, kind of to do the hello world of music, and make a block that
Snap, 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 snap.
and now I've manipulated and made music. Or you know, if I'm, you know, let's take this thing, and actually I'm just going to record this one. Oh, did it actually work? I don't know. We'll see. Did it work? Let me try. Okay, yeah. Okay, good. so we sounds a little bit cheesy. That's because the formula isn't quite right. This is a formula that an actual kid came up with. You could do the math to get it really right. How to get it's not easy to do with the octaves. So we can interact with the real world. We can think about impressions that we get, and we can think about computational concepts. And so my message here is that there's a world out there that waits to be discovered. And if you're waiting at the entrance, putzing around with things like loops and variables, that's underwhelming. You're going to lose the beauty and joy that waits behind the door. So don't be the gatekeeper by making people only enter if they get these concepts. Let them do something. Let them discover something. Let them discover kind of the real concepts which are more relevant to them. So okay, this is the fun stuff. Now it's going to be a little nerdy. I'm going to make a new project, and again get the half block. Here's the half block, the double block that I made before. So I can use this double block, in the kind of way how it works on functions to make a little encryption procedure. So I can say I can get the Unicode of a letter. I can also get the Unicode of a string, and that is going to be a list of letters. Remember, it takes any data. So I want to double this. So now I'm getting another list of numbers, and I want to transfer this back into letters after I've kind of shifted it. So now I'm having kind of this funky thing, and I want to output that again as a string. So I'm joining this. So this is a little expression that kind of encrypts something. I turn this expression to a function, and one way to use this as a function is to use one of these blocks. So I'm saying join this, and I want to leave this empty. Remember, it's the formal parameter. So now I have a variable that has this function, encrypt, and I can call this function, and I pass in whatever it wants to encrypt, hello world, and I'm getting this. So I'm making another variable. That is my secret. Setting the secret to this, okay? So now here's my secret, and there's a function. And don't make an encryption that secret algorithm. This relies on a secret algorithm, and I'm going to show you why I've made that law, because we want to think about functions. That's one of the interesting things that these rings let us do, that we can, split something, and then we get its components. We can also split a function. We can split encrypt, but we want to split it by the blocks. And now what we get is a syntax tree. So this is now we're analyzing syntax. And folks, when we're talking about syntax, You know, we're not talking about semicolons or commas or curly braces or brackets. That is just decoration for the parser to take out. What syntax is the structure and rules that get to a function and what you need to pass. When we say something has syntax is hard, what we really mean is, you know, these stupid characters that, you know, some computer program needs to make sense of. They're hard to memorize. But syntax really isn't so hard. Syntax is just kind of how stuff belongs together. And so we want to be able to think about syntax, to think about the structure. Another important concept. So here's a function that is actually a chain of monadic functions that all have one input, and that's an easy way. So it's really just a sequence of things that are nested. So I want to turn this into a sequence. I've made this, I can write this myself, that just, you know, unravels the tree into a list of functions. So I have the sequence. Now I have the sequence of blocks, how they're called. So what I want to do now is I want to make a function that takes another function. I want to make a function that takes this hammer and makes this pair of pliers from it by just looking at the hammer. Okay, so how do I do that? Usually what you do, you have a function with x, kind of never mind, we're just going to reverse the list, right? We're just going to do it backwards. So now we have a list. I'm going to reverse that list. Now the sequence has changed, but that's not going to invert the function. Now we also need to find the opposite of every block in there. And I've kind of prepared that. There's a little block that gives me the opposite. This is how I made it. It's just pairs of blocks. Give me the other. And so what we're doing is, again, we're using a high order function. I'm going to map over this, the opposite block. So now I'm getting a reversed sequence of opposite blocks. So what I want to do is I just want to stack this again. I'm going to stack this again. Now I'm again getting a syntax tree. I'm going to put this together again by joining this list. Now what I get is a new function, new tool. So what we're really doing here is, I hope you realize, is we're on a meta level, we're doing algebra. We're actually making a function that gives us the inverse function, and we can take this out of here. So we've made a function that generates a new function. I'm going to call this new function with a secret. Pass in the secret. And I'm getting hello world. Folks, I don't know whether you're kind of aware of what you're seeing here. This is really something where we not just think about solving a problem, but where we think about how to solving the problem. Because we've made an algorithm that reverses an arbitrary function just by looking at its structure. And so this is something where I say, you know, this might be slightly more than a tool, because this is a tool that can think about itself. This is a tool that can generate other tools, arbitrary tools. So the tool itself is really just an input to the thing, and it can output a tool. So this is kind of the meta thing that inspires me. But all of this is kind of, you know, a little bit nerdy. I want to end with something that is kind of more practical. So when we tell kids, you know, this is how you do media computation, deal with data, sooner or later they ask us, yeah, but how does it work in the real world? And then it's not enough when we show them, oh, you've just done it, you know, with the data set of 2,800 records. They want to do it with real data. So I'm just going to do something with real data. Real data has a problem that the interesting data has personal information in it, and we can't use that. So we take dead people's personal information. This is the data set of the passengers of the Titanic. So we can find out interesting things, and usually, you know, so this is a table. It's just a list of lists. We can use higher order functions on it. For example, we can filter it. Filter is keep. We want to keep the items from the Titanic, for example, all those that have survived. So where there is a 1 in the item 1 of the Titanic. And now we get, you know, these are all the survivors, and we can see it's 342, and we can do all kinds of analysis here. You know, the usual stuff. What's the relationship between gender and the chances of survival? What I'm interested in is, you know, how they and the names. I want to know the top 10 names of people, first names, because this is 1912 after all. So we can also import other modules. We have a frequency analysis module, and there's another concept of that, you know, if we chain things together, it's a pipe of things. So we can get the Titanic and now have a chain of functions that each, you know, the next one. And so first I want to, you know, keep all the ones that are male. So I want to get all the male, and the gender is, I think, in number 4. So now I'm filtering it. I'm only getting males. Now what I want to get is all their names. That's in the 3rd column. So I'm making another entry in the change in the pipe, and I'm saying this is item 1 of not the Titanic, item 3. I'm just getting item 3. I'm just getting a single record, but I want to get the whole column. So I'm saying, you know, I'm getting the column of it. So now these are all the names, but there's more in there than just their first names. So what I want to do is I want to split this up by words. Now I'm getting another kind of, I'm splitting up this one column. What I'm interested in is the second column of this. So I'm just duplicating this, getting the second column. Now I should be getting only the first names. Yep, wow. So I want to analyze these by their frequency. There's a little analyze block. So now I'm getting a table, each name with the number of occurrences. And in order to get the top 10 list, I want to sort these by the second column. And here's the you know, top 285 list of names on the Titanic, male names. First one, William, John, George, Charles, Henry. That's what you would expect. Now the interesting thing, I show this is, well, what about girls? Let's find the top female names. So what we do is, instead of male, we just need to filter for females. What do you think is going to be the number 1 female name? Excuse me? Elizabeth? Excuse me? Sarah? Any other takes? Jane. Okay, watch this. Elizabeth, Jane, Mary. It's William, the number 1 female name in 1912. So what is wrong here? And you know, then there's Anna, Mary, and there's John. Then there's Thomas. So did maybe filter not work? You know, let's debug this. So I want to keep all the, you know, so yeah, they're all female. But look at their name field. The data isn't wrong. The data is the actual list, is the actual passengers. The algorithm isn't wrong. What's wrong here? Nope, there is not a, it's not a, the married women go by their husband's name. Remember, this is 1912. If you were married, you were basically under the power of your husband. So the bug that we have here is not in the algorithm, it's not in the data, the bug is in society. Anybody know when in Germany, I'm a lawyer by trade, so I know this. When in Germany, women were allowed, married women were allowed to take up any job they wanted without their husband's consent. Okay. It was actually 1977. So get this. So we have a bug in society, and so in order to find out the actual top 10 list of female names, we have to go to much more. We have to write a much more complicated script. I've prepared this, and this is another thing. So this is now the much more complicated script that kind of does some conditionals, some embedded pipe. And then we get Anna, Mary, Elizabeth, Margaret, kind of beautiful names. Florence, you know, look at this. Catherine, Lillian, Honora. But here's an important lesson. Sometimes we think about, you know, another group of society, another gender to be complicated. Because we have to use a more complicated algorithm to deal with that. But it's complicated because we made it complicated for them. And so it comes back and haunts us to be complicated for everybody. So this is something that really segues into the idea that, you know, watch out what data you're dealing with. Watch out the context of the data. There might be bugs where you don't expect them to. So this is a bug in society. So I want to close this with just showing this one project that we made for the Wissensfabrik in Germany to think about machine learning. So this is a curriculum you can actually get. This is about machine learning. This is all happening in Snap. We show you how you can write that program yourself. This is a gesture recognizer that you can program yourself, and you can use the gestures that you recognize to animate it. So we can say things like, you know, what if you draw something, and what you draw isn't just a picture, but is something that you know, the program recognizes, and it sort of becomes a symbol. So we can have the computer actually understand what we do and use it to teach stories. By you know, making unexpected things happen. So this is this kind of, you know, emerging technology that's not that emerging of artificial intelligence that we really don't know which shores it leads us up to, and we have to be really, really careful which data we feed it, how we train it, because when we made this, it didn't recognize my colleague's handwriting because she is left-handed. So be careful that you always train it such that there's a variety of, you know, gestures and of data. So the idea really is that, you know, maybe in the future, we are just going to build some of those tools, but AI is going to help us really deal with these tools in ways that we didn't deal before, so that our applications not only become artificially intelligent, but maybe help us learn something about ourselves and to really become empathetic and to understand the differences in our society. And thus becomes a medium for us, not to understand how scientists work or how computers work, but how we interact with people. Thank you.
Thank you very much for that inspiring talk. Short questions. If there are some from online, can you please?
Thanks a lot for super nice presentation. I want a lot to know what you is even all this amazing technology of, in this case, we have programming. What's, in your opinion, future of textual programming? Considering the visual images that are
Okay, so the question is, what's the difference, or what might the future of text versus blocks or visual?
The future of textual programming, just
Yeah.
programming by writing code.
Mute.
What?
Well, I'm a blocks guy. Evolution of visual. I'm a blocks guy. I don't think there's any need for textual programming. We just use text because that's the only thing we have. Because keyboards have been around for over 100 years,
so every computer already has one.
Also, I think the distinction between text and blocks really is a false distinction. What I've shown you today is not really so much the difference between text and blocks, but between a live programming system and a dead one. So dead programming is that what we teach to kids. Dead is rigorous. You need to plan in advance. That's what computer science is. You need to have a pencil and a pen, and you need to goddamn get your issues before that. You need to get concepts and understand them, and only then you're allowed to design them, and then you get this error because you were wrong, and because you're not made for programming. And so the difference is, like, we have to allow ourselves a more playful approach to experimenting, to not being scolded by the computer. So I think what I've shown you today, Snap, Scratch, so it's a live programming environment. That's much closer to, say, Lisp or Smalltalk than for example, App Inventor is more like C++. So the main difference really is that liveness. The other thing that I've shown you today is abstraction. Abstraction is something that is hard when you encounter in language, because in regular language, it becomes very difficult. If you have an abstract thing, you might not recognize it. It tells you right away. In computing, the other way around. Abstraction makes stuff easier because it unburdens your mind from thinking about loops, variables, indices. Because you forget about that. So abstraction is your friend. The more your abstractions, the better your abstractions are. So the farther you get, the more you get to find that day with the interesting stuff. So to answer your question, I'm programming text every day. I program anyway. I don't care. I love visual programming. I think there might be other things that are yet going to be discovered. The idea really isn't the modality, but the abstractions it is. And we should be very, very careful to take for granted that the one imperative way that uses loops and variables is easy, because it's not easy. It's really, really hard. Because nobody thinks imperatively. No kid and no adult. Only, with stupid stuff like, peanut butter and jelly sandwich. But anything else, we think in rules, we think, in more abstract things, because otherwise our brains will explode. So I think it's about abstractions, and a visual programming language has the huge benefit of making abstraction visual. You don't get any cryptic stuff. You can see the block inside the ring. So I think that's a huge benefit.
Thank you very much again.
Thank you.